So the time now is okay. This stage is in single protocol here and now forever. But literally, I've just got the protocol ready. But the protocol is for here and now forever. So I'm using web camera audio to match this phone. So let's get started. So, NSIGGI here at Google. NSIGGI, N for November, S for Sarah, I for Indigo, G for Golf, I for India. N for November, S for Sarah, I for India, G for Golf, I for India. On github.com/O for Oscar, B for Bravo, I for India. N for November, E for Echo, X for X-ray, and U for Umbrella, S for Sarah. So the NSIGGI protocol is here and now. Erratic. So we got the secret protocol, a protocol for communication, for acting, for interception, intermission. Let's look at intermission. Definition: intermission. Intermission means on-the-fly action. On-the-fly communication, editable. So can real-time communication. It works like in real life. You're directing like a secret intermission, and you got interception. So interception is on the fly. On the fly means while the system is running, executing. Inter means you can intercept. So you get interception. Then you get intermission. You can intercept the communication channel. You can intercept because NSIGGI is like a basically human rights protocol for safety critical sparse safety. So how does NSIGGI work? How does NSIGGI work? NSIGGI is a sparse active interpretation. So here's a sparse model of data types and data information. You got trident data, trident information, and trident kind of information. Because you got in Rift, it has a token type, a token value, and a token kind. But the trident has a token type, a token value, and a token key. A token type, a token value. The type has a type of value of a Rift token, which is matching kind of system. Then token type give you token kind. If you calculate it as, if it's as, it has a kind. If it's as, it has just one entity. It means one entity, one classification. If it's as, it's to two or more classification. If it's as, if it's token kind, it has a kind, but it's used to it's used in a heterogeneous, homogeneous set, homogeneous first to heterogeneous mapping of coordination. Because the as keyword and the is keyword are dynamic type resolution for the trident system. So what that means, you got an interpreter. The trident sparse model means you can model things, any model a data structure or some kind of data, trident data, trident division via interpretation. For example, yes, my yes is your no. My no is your yes. My maybe is our shared data. We share maybe within this year. So it's basically a permission, because a permission, consent, and consensus system for trident evaluation, trident what we agree, what we share. For example, if I nod my head up and down, you can agree that's a yes. If I shake my head, no. If I spin my head round like this, that means maybe. But but that's too kind of ambiguous. So I would just give a shrug and can agree that's a maybe too. In our framework, what is a maybe on our officer or body language? Body language, yes, up, down, shrug, no, maybe, I don't care, maybe. But like maybe, and no, like maybe it's called freedom. But the shrug is used as instruction to determine whether we're sure. So the shrug is not rude, but it's a rude maybe. Because we consent to both maybe. A yes is a one, a no is a zero, and a theta is the theta symbol is a maybe. And how this works is basically NSIGGI gives you this model, use model to solve the problem of NSIGGI. NSIGGI. N for November, S for Sarah, I for India, G for golf, I for India. Yes is one, zero is no, theta is maybe. So, so so how does the NSIGGI work? Okay, the NSIGGI works because so if you can picture this nice 1, 2, 3, 4, 5. So the NSIGGI works because of the model. So you get an X object. So this is an X object. So get a 1 and then a 0 on epsilon, or 0 or epsilon, or 0 or epsilon, a 1, and that gives you a 1. And that 1 goes into an epsilon exclusive of 0. So you get 1 or 0, 1 or epsilon, and then a 1, which is a not, which is an XOR. Or you get a 1. So you get a 1 based on the combination. But then you get a 0, then you get a 1 next. So if you get a 1, you get a 0 next. A 0 or 0. So 0, 0 is epsilon, zero, you get zero or zero at the end. Because the XOR operation preserve the state. So you have to perform the OR operation and to do this as a sparse state machine. Because this goes from one state to another and get a 0, 0, 0. So why does this work? This works because you get maybe. So if you do maybe, so you get a 0, 0. You compute all the matrices as possible, and you have to complete the shortest path. So the first problem is to take the this kind of way. So if I have the sequence of bytes, bits, or six bits, one, 100, maybe, which is theta, one maybe. The message has preserved itself because maybe is a valid solution in between 1 and 0 that we don't want to polarize. So the B share maybe, I'm sending maybe, and maybe is theta, not epsilon, maybe, because epsilon refers to sister. So my maybe is your maybe. Yes, so maybe. So your is my halfway here, but my epsilon is should be your epsilon too. I have to flip it. So in this case, the XOR position will preserve the maybe because AB is a maybe is two vectors, which is one matrix. You have to multiply by a matrix to get a transpose. You have to transpose the OR, and then you have to flip some. For example, something like this. So you get, so if I'm sending this message here, 100, 100, 1000, I can develop this matrix here. This matrix here. 100. I'm sending 100. I am 0, send this message here, and this message here. And this message will be so if I get 100, I get 101, 10, and get 00 and 1. So I get a vector of 4 vectors, 0, 1. Another vector 1 to 0, and you get another vector 1 1, another vector 0 0. Those are the 4 vectors I get. The 4 vectors I get that I can multiply to preserve the maybe. But they have to share a path, and the path of this is computation. You perform on a vector, so you have to perform. You have to operate. So the maybe has preserved on a vector, and a vector is what keeps the same. So the vector is so if you have information, if you have information, 100, 100, you are preserving 100, you're preserving 100, and the 100 you're preserving is basically a trinomial. So we have to send in 2. So the 100, I have to send 1, 0, and then send a 100, and then send that one. So if I send is 100, I should get if I multiply by the path of this matrix 10, 01, 10, 01. And 1 or 0, which is a vector, 0 or 1, 1 or then 0, some kind of path to make it. This is a dynamic programming. The shorter path via dynamic programming gives you this kind of sparse matrix. But if you're watching what dynamic programming is about, this is the shortest path to get the fastest result, get the matrix. So this is a dynamic programming problem via polarity. The way but because it allows you to use memorization and tabulation, which is a bottom up to prevent recomputation of a table. So you're creating a table ahead of time. You create a dimension, which is the vector, you have to define and this is the encoding table. So the encoding table is basically the vector. This is a dimensional game because it's a vector. It's basically a vector. So this vector table is 0, 1, 1, 0, 0, 0, and 1. And this encoding table you have to multiply maybe to which is XOR operand. To get the maybe back on the other end of happen. So for example, you have maybe can be yes or no. So if I multiply, if maybe is no, maybe is no, I get the matrix of 0, 0, 0, 0. But these are two vectors that flip the 0. So if I start with 0, so maybe 0 is 0, maybe 0 is 0, and then maybe 0 is 0, and then XOR 0 zero, you get a zero, and then maybe zero is one. But these are the maybe zero is zero. So if I multiply this one zero, but so zero, zero, but if the message is zero, I just have to take that part automatically because it respects dynamic position, which will be the stabilization is bottom up. I start bottom up to get the table using a self balancing tree, bottom up tree, and the BF the breadth search to resolve the problem, which is like a Cisco model of kind of inter, intermission to solve the problem as you know as new solutions emerge in that framework of time. But until the transit system can work in normal framework. So the matrix here for if the matrix zero is zero 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 zero, and the matrix is already encoded if the matrix is zero. So it doesn't have to see guess again if it's if you're reconnected. So if your maybe is my zero, I have to. If you say maybe and it's my zero, you have to. So how is it work? Is like if you have a server and the server says zero, that means your zero is my maybe. But you know, I'm saying maybe. So this is usually so if you're saying zero, and you say maybe, and I'm saying maybe. I'm sending you my zero. And this will get confused. So this will get looked up. But you know, when I say maybe, I may mean yes or no. But you know, I get zero zero zero, zero, and I give that to you in your encoding table. But if my maybe is a one, I get a one zero, and I get one or zero, 1 comma 0 in a vector, and then a 0 comma 1. I get a conjugate opposite pair, which is the 1 0 0. So that means coming in 1 in this context. When I switch context, when I switch what I'm talking about. So that is the goal of this. So you got the final one. So yes, no, maybe is the consensus metric for it. So then so you get this kind of thing. You get this kind of thing. So you get as 1 0 0 0 1 because so you get so you get so if I was basically the only thing about the matrix is basically it's a triangle model. So if I'm sending 1 0 0 maybe 1 or then 0, I'm sending through a medium, and that medium works on. Come in. I'm busy. I'm busy.
Yeah, just a goodie. I'm giving you a goodie and I go.
Oh really?
Yeah, just a goodie, then I go, yeah?
Thank you. I love you.
Thank you. All right, I'm going to shut your door now, yeah?
I love you. Thank you, Elijah. So it's basically a sprinkler. So the spring is there, and the spring works the system of spring. So if I put a spring, it has potential and kinetic energy, and the potential energy has a ratio to the kinetic, and that's the second part because it's an echo philosophy. So before getting echo, you have the amount of force you put in to scream to send a message, and that force is potential and kinetic. Because if you have double, if you then send a message, you are applying double the force, and that's what you. So the next step is potential. I haven't got a formula. So basically, force equals mass. Force equals this is work done. So you have to in the physics, energy and work done. So I'm looking at what is found. So energy and work. So work equals force times distance times cosine square. But you know the work is the angle, but when it is zero, the work is, so I'm saying to you the work of a system in a system of messaging because the work is 200 newton times distance 3 meters times cosine times angle you're pushing out, which is 20 degrees here. The work is very important because 200 newtons times 3 meters times 0.9397 work to the nearest is 500 and 64 newtons meters to the nearest meter. So work equals 454 joules. Without cosine theta, the wrong with joules. Okay, so the wrong with joules. So this is cosine. Let me just work it out. So it works on this principle. So if work done, so in spring physics we have half of it. So you know if I put half the potential force, I get one full force. So it's a half. So if I put half the force and pull it, I have the opposite force of kinetic. So you get potential force and kinetic force, and that will be one full force. So if I have one, so that's what happens. So if I pull will double the force. I have a spring. So double the kinetic force is you can get four. You get the ratio of four. Double the kinetic force. I get four times the force. Double the force. I get so two to the power squared. Two power squared. To the power of m. So because the force is two to the power of f. So if the force is a half times a half to the power of two. So one half to the power of two. No, one half to the power of four. One divided by two to the power of two is okay. One divided by two to the power of four. No, one divided by two times times four. One divided by two times four. Basically one divided by two. So you get the force. The potential force is what? The force is so basically if the force in newtons is one of 50 newtons, and the victory force or bytes, whatever, or basically this will do 50 bytes per minute bit rate. So basically, I'm trying to use bit rate to calculate a bit rate because I have to do it properly. Bit rate. Basically, bit rate. So if I use bit rate, so I'm used to calculate bit rate. So bit rate. So bit rate is very important. What is a byte? Types of bit rate. So constant bit rate, variable bit rate. So how do you calculate the bit rate? So bit rate is calculated from a number of bits divided by time, number of bits times seconds. So 500. So this ratio, so the ratio of bit rate is the same what you calculate. So if you use bit rate model, so I'm trying to do. So the bit rate was 5 MB equals 40 megabytes since 1 byte per 8 bits. So that's basically what so the internal part has to preserve this via the processing mechanism. So if I want to do it, so I'm gonna use the example of 40 I'm gonna use 40 megabytes divided by 10 seconds, which is 40 bytes per second, and that's the bit rate. Because if I'm sending let's use 25. So we get 40 megabytes, which is the megabytes, which is like 40 megabytes. Let's use like a 500. Let's do like 500. So let's use 50 megabytes because 50 megabytes is a tenth of 500. So 50 megabytes over 10 seconds. So basically, this would be zero point 0.5, this would be 5 megabytes per second, per second, which is the bit rate. So this is the first bit rate. So this is it. So this is the first type of bit rate, which is a system of processor. So in this in the work philosophy of work done, I have the force of I have double the space. So in the force I'm trying to apply is what I'm going to send it. So the force of this will be the work I'm doing. So if the distance of the message is not important, I have to solve for some kind of force. So I have got the minutes per second. So I'm not trying to solve for the force and distance. But distance is of course so the path is decided already, which is cosine theta. But in the kind of framework of so the 3 meters. So we have if you have like a I'm sending for 15 meters, 15 meters distance in over 15 meters. Then have the force, and then the force, and then the force is 10 meters. The force is 5 meters. 5 meters. The force. The force is what? The force is double, and the force I'm using it. So if the bit rate is 5 meters per second, I have to double my ratio. So basically, I have to double the space and double so my force will be double half the time. So basically, I have to have double the force instinctively. So I have to have the force to be double. So double the force will be 100. So I have to have space for 100 megabytes. 100 megabytes over half the time, which was 5 seconds. So this is my first bureau. So this is the sequence of so 100 megabytes over 5 seconds. So 100 divided by 5 would be 100 divided by 5 100 divided by 5 will be 20. So you get 20 megabytes per second, and this is the first processing style. So this is it. So I get double the space or half the time. So percent, this is megabytes. I'm expecting for this 20 megabytes per second to be my best case. My best case for the space I'm storing it. And for the opposite of the best case, we have the 10 times to 20 megabytes, 20 seconds divided by double the time, which is 1,100, which is 5 times 2, 50 times 2. So basically, filters will be 100. So you get 20 seconds divided by 100 megabytes, which would be 20 divided by 20 seconds divided by 100 megabytes, would be 0.2 megabytes per second. And that would be the force of the two systems. So this part are the value part can take via the processing mechanic of the system. Because it's a human code. So what it means literally is have to calculate. So I get two of the two one will do, two ones will do. So I get 100 divided by 100 megabytes divided by 5 seconds, which would be 20 megabytes per second. And I get 20 seconds divided by 100 megabytes, which would be 0.2 megabytes per second via the space and time. Space first and time first, auxiliary paired. But these are just two parts, but there are four parts I can take, which is AGG type. If I prioritize the space, if I have, so I have half the space I can prioritize, which would be 50 divided by 50 divided by 2. So I have 50 divided by 2, which would be 25. 25 over double the time, which would be 20 seconds. So divided by 20 seconds divided by 2 will be 1.25 megabytes per second. This is basically AGG type 2, type, really, type 2, which is half the space I need. So this is it. In the worst case, you need half the space. So no, this is half the space. So I'll get half the time, which would be 5 seconds divided by double the space would be 20. So I have 25. So basically I have this model here. 5 divided by 20. So I have 5 divided by 20, which would be 5 divided by five 5 seconds. So this I have 5 megabytes divided by 20, which is double the time. 5 megabytes divided by 20 would be 0.25 megabytes per second. And I have the other one, which is 20. 20 divided by double, half. So half the space, I have half the space, which is 25 divided by 25 bytes, 25 bytes divided by 10, 25 megabytes divided by half the time. That'd be 5. And that will be 25 divided by 5. It's 5 megabytes. So, this is what I'm saying. To get 50, 25 divided by 10, 25 divided by 5, 25 divided by 5. And that'll be 5 megabytes per second. Okay. So in the worst case, the range is 0.25 to 5 megabytes per second. You have to compute. This is just part of the worst case scenario. So the work done is for a bit rate. So the bit rate of the engine, so the work done is a force you have, and the force can be the little force you have, so the force will be how double. So the force will be 200 newtons. The force of the message. So we can have the distance of the message, but distance traveled will be So this is we're trying to use a polar coordinate system. So the distance traveled based on the force is basically so car so basically this is tangent line and cosine. Because the basically the goal of the whole thing is to double the message. Because if the message bounce off the medium instead of the medium, you have a spring, and the spring just sends the message, and that spring has the message sent, but can recover the message via a polar rolls. So the polar rolls was saying because so the bits per second advice. So you get the force and distance is let's say you send a message over 3 meters, 3 meters, 3 meters, 3 meters let's say 15 meters, 15 meters, and the force again you're applying is just there's no force applying there. So if you have a flow, so the work is basically so you trying to calculate the force. So let's rearrange. So force work equals force times d, so times c cosine theta. So the force is basically divided by c. So basically, I'm trying to get the force. So the force will divide by c. So divided by c, and that'll be work divided by c equals force times d. So the work done divided by the kind of cosine square, and that'll be divided by d, which will be the force. So work equals the divided by c divided by d. So so it's like I said. So you get work. You get a distance. So distance force equals work divided by c divided by c and d. But this is not making sense. G times d divided by 4. Okay, but let's do C times D. You get C times D, which would be C times D. Force, work equals, force equals work divided by the kind of the coordinates times C times D, where C is the cosine times D. So the work. So this formula is a half. So this is what I'm going to use to do it. So if the angle is cosine, the force is what you got to apply. So the work is literally the amount of calculation of verification because the work is very important. You need to so you get the work and get the force. So the force you're gonna put in to send a message is literally your fingers and put your fingers upon it. You're gonna put some people because the work is basically what calculation. If you can verify the work is done, you need to check. You need to check the message again. You need to recover the message. So say it makes it really simple. It's on the fly verify. So the try so you send two bytes. So everything in triplets. So because the triplets is basically you can resolve with a parity or you can try to be between the maybe because you have 100 which is like can be covered if there's any kind of Hamming code incorrection on the fly because this works. So the formula you gotta use is force equals work divided by the kind of SOHCAHTOA cosine or times distance, and distance is just a start distance in the real world. So how does this work? So if the message again, if the message is what? If the message is 100, and then maybe 10 theta. You send a message you send the message 1 0, 1 0, and then 0, and then 0, and then 0 becomes maybe, takes the part of maybe. You have to resolve the part of maybe because maybe can be 1 or 0. So if you have 1 or 0, 1 0, which is because it may be 0. So basically, you have a self-balancing tree. Basically, sorry, so this is my working number 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, 5. Basically, here is basically an echo chamber. So you said echo it bounces off the walls. The walls are literally just the kind of things that can stop the message from getting to the system. But this message has to go and be controlled. So and the chamber is the message. So this message is basically what the chamber is. You can send a message across the region. I'm saying here. So the goal of this is to have a self-balancing tree that resolves the tree, which is called an AVL red-black tree. Pruning, because the red are pruned out and the black are kept. Because you know the other way around. So the red and black, because red are temporary information that will cover the data, and black are this is an AVL tree, self-balancing tree. So you get a maybe. So if you get a zero and you're getting a maybe, and this is not sure, it's really lost the truth table. So it has to basically you look at the truth table and get the right one, which is a one. And the one is basically what it is about. You get a one, and that one is what it says. To get a zero, it takes maybe a one, which on the right node, right root, left evolution, which is Cisco model. So you get a maybe if you get a zero, if you have a zero, and if you get 100, and you get a one, and that one, you get some kind of disconnect, and the system gets a one on epsilon. It has to have some kind of unsurety matrix, which it has to be unsure. So it's unsure what the value is. So you have to you look. It says one. It says one or zero, and one gets sent because it's a two. This one work, but if it says three because it says three because they can resolve itself because they are trident. They are three informations that can have three interpretations, and three interpretations can give you the full information, like yes, no, or maybe, and that's why this is a trident system. So if I say it's 1 0 1, and I get a zero, and I get a, and then I say the next is 0 and 1, and then 0 and 0. I should be able to look it up as a maybe, and maybe should verify it's a zero. So because the zero is basically was so you just go from some kind of a matrix that gives you the information at the full statistics as well. Oh, so the maybe is very important. So if you have maybe get yes and no on the left node on the right node you get yes no. So you understand. So that's what understand how that works. So this is what we call sea urchins. But sea urchins have dendrite. So the information of the schedule is basically a half or 4 to a half because there's the close sequence equation. The dendrite flows information through the data and touches the urchin, and the urchin literally preserves that information. But that's basically how the system because the urchin is the central information sometimes. So they're literally open motor because the oceans don't need to are living through the blissful. It's like that. So it's like that. So the goal of this is to have the work done. So again, the formula really according to the formula for work is work equals force times distance, and work equals force times distance times the angle times the polar angle. But if you have if you use different force, the force is basically if you have a pulling force, you have a pushing force. So the pulling force is basically I'm about to send it, or I'm ready. So it's in a state to send. In a state to send, in the still system. If I push it, if I then leave it, so if I pull it, I don't send it. I have to consent because so I can just press enter, this which is send, but I can pull the string and push it and then let it go, and that'll be a send. So if you pull a coil or coil of spring, you pull it up and the coil lets go, it bounces up with double the force because that medium is the coil trident coil. So you get work equals force times distance times cosine, and you get force. You get force equals work divided by cosine times times distance. If the distance is 115 meters, then you get the force of pulling to push him. So if I have a pull force, I have a push force. So if the force I have is half half the force. I can determine the work done already because I'm doing double the work. Sometimes. So make the force a parameter. So let me find out the force. Let's make the force object. The solve equation. Listen, I'm trying to solve this problem here. So how? No, calculator. So the force. I'm saying, what is this? So I have a little more time left. So let's make 15 minutes time, and I do the calculator. So the calculator will show me. So the cosine. So if I have the message one. Because if I have the distance 15 meters, 15 meters would be 1,500 because 1,500 1500,000, 15,000. Let's call that 15 meters, which would be, because it's 15 meters, it is 1500 meters, which would be 1 kilometer. It's 15 kilometers. So this is very well 1 meter. So 15 meters. So I'm going to use the times this by the cosine of trigonometry of cosine of this cosine will give me the polar axis of x, y, z. But I'm going to use the cosine x. So this will be cosine x, which would be minus seven. This would be the cosine x would be minus 7,000 minus 7,500. But this would be three periods. So I know give the work. The work is one. So the work is one divided by. So because I haven't got the work, I haven't got the work done. So let me do that. So get the 1,500. 1,500 times cosine times which is the distance, and that distance is 1,500, and the cosine will be, so if I then calculate the cosine, because cosine will be 0.5, 0.5, 0.5 is the cosine, cosine of 0.5, and then we get the 1,500, and then we'll times by 1,500 times the sine, 1,500 times the sine times the sine. That will be 0.8, 0.8667, which is sine, and then we get a tangent. Tangent, so we get a 1,500 times 10 times 10 times 10, which will be 1.732, which is 10. So this is to get the y cosine of theta. So you can get y over x, which is y over some kind of angle x, but that'll be the arctan with two parameters, because they take you get the cosecant and the arc inverse cosecant, but so the work there will be a half. So if the work here is that will be the force times that will be the distance times the angle xyz, based on cosine, sine, and tan, and then the equation also and get then you get the distance, the force. The force, if the force is so how do you call the force? The force is basically 200 newtons. So the force will be half, because half the work. So basically, the force will be how I get the force at 200 newtons. 200 newtons will be half the force. Where theta is angle of force. Because you don't need double the force, you don't have the force. So if the force to send a message is double speed, the force will be log n force, half the force, half the space. So because you don't, so half, if the space is so the iota force will be half the space, and half the space is if the space is 100. 500 kilometer, 50 kilo, 50, 50. If the space is what, 50 megabytes, the force is half the space, and that will be 25 megabytes. 25 the how was 25 over time, space of 25 over time or 10, 25 so it could be 25 over 20 over time over half the time. So you get half the space, so that'll be 50 divided by 2 be 25, with 5, 50 divided by 2, 50 divided by 2, 50 divided by 2, 50 divided by 2 is 25. 25 divided by half the space and double time, or half the time divided by double time will be 20 divided by 20. Okay, so 50 divided, 25 divided by 20 will be 25 divided by 20 will be 1.1.25. 1.25, and that will be the force. So the force is 1.25 newtons, newtons. But this force is basically the full force. It's 1.25 newtons, newtons of force. So obviously, I am now have to multiply this by 1.25, and that will be this function. So this is not work so far. So I'm trying to multiply. Right, I'm trying to multiply the XYZ here by 1.25. Okay, so you get 1.25. So you get 0.5 for the sine. 0.25 for the cosine. The 0.8886 0.8667 for the sine and 0.723. So this has to multiply by the cosine, which would be 1.25 newtons. Uh, so 1.25 newtons will be so 1.25. So we get 1.25. So basically 1.25 newtons. So 1.25 newtons times point 0.5, 0.5, zero point 0.5 in degrees will be 0.5, which will give me the force, the work done of 0.625 in exponential, which gives you 0.25. So you get 0.625, and then we get 0.26225 of force when of work. This is the work done. When the when the sine is when the cosine is 0.5 and the cosine is 0.5 and uh, so we get 0.865. So we get 0.8686 0.867 times, which is the result of the sine, times um times the force times 1.25, which will give you newtons, which will give you 1.80 let's see, 1 point 1.80083375 or 1.804 1.804 or 1.804, which would be the force in newtons. So this is the force. So the force is approximately 1. And you get that's for the sine, and you now get the one. You get 1.732 times 15, which is down, times 1.25, 1.732 times 1.25, which is 1.732 times 1.25, which is 2 wait, 2.165, which is a tangent measurement. So you get that. So the kind of am I so working? So basically, you get 44 minutes. So I get this angle. So I get this result here. But this is basically what I've measured. So this is trying to measure. So basically, when I say this is work done, so I have the work done. So if I double my work, that means I got to. So if I have double the work, so basically how I verify this, basically, how I check is basically because work is very important in computer science. So you get the derivative, the force times the plate of the system, and they work by the so this kind of the system is basically working on the spring force. So I am now using half the space. So if I want to now verify, I can use so I have to send two segments of this information at this rate. If you're able to get information, so I have to take double, but I can just send 1 unit of it. So if the force was this is a force of 1.25, which is just one force, 1 full half force, which is like 1 full half force. But if I double the force, which would be 1.25, 1.25.2, I should, only need to send it twice. So, 2.5 is basically 2.4 due to the force. I need to send it twice to make sure the measure. Oh, it's something. If I come to 2.5, that'll be the same thing I'm doing. So this one said, because it's really what I'm saying. So the kilojoules matters because it's 2.5 newtons. So if I use the efficiency, efficiency is how much energy is useful as a percentage of the total. So useful energy of a total energy as a percentage, and that's what you're gonna measure. So if the efficiency goes down, 40 meganewtons. So if I have the energy I sent and the force I use, I can verify the force is efficient. Because the efficiency has to matter. So if I have work divided by, because I have then the force I'm gonna apply is efficient in bit. So the force equals work, which is 1.25 divided by the constant time, which is sine, cosine, which is 0.5 times the displacement, the distance, and this is the displaced. So that would be the cosine will be any angle from 0 to 180, via A to B. So so 0 to 180 could be a linear path. Which would be a statistical model of the really short path, the shortest path for dimensions to travel in the regional units. Because the cosine represents the dimension of x and the y. So the Iranian function has to travel in basically double the space and half the time to relay the information via signaling. Thank you guys. I get 3 more seconds.